We're going to be picking up with our applications and algorithms section, and we're going to be led off by this by Dr. Tom Quinn from University of Washington, Seattle, who is going to give us the latest information about progress on the ChaNGa project, which is one of our long-term collaborations. Thank you, Tom.
Okay, thanks. Got it. Yeah. All right. Thank you for having me speak here. So I'm going to be talking about this project we've been involved with for 10 years, nearly 10 years now. A computational cosmology Treecode. There's a cast of thousands who've been involved with the development. Former students of mine from the University of Washington, and former and present students of the PPL. As I was explaining to people at dinner last night, we have significant evidence that the universe started out with the Big Bang, and this is one of the primary pieces of evidence. If you have a television of the pre-2005 era, you turn it on, there's this noise on the screen. That noise has a certain temperature, about 2.7 degrees Kelvin, and it's coming from all regions of the sky. And if you map out that heat in the microwave at a very fine level, you get this map. So this is a map of the entire sky. The sky is very even to 1 part in 10 to the 5, and that's what these the colors here are representing. Variations in the temperature of the cosmic microwave background that are 1 part in 10 to the 5. From the temperature, we can, and a little physics, we understand that this was produced when the universe was only 380,000 years old. And the temperature fluctuations are telling you what the structure was like there. And basic answer is it was very smooth. But what we also know is somehow this very smooth structure somehow turned into this. This is a map of the nearby galaxies, where nearby means about get the number right, nearly 1 billion light years. The Earth is at the center. Each point here is a galaxy, and you see the galaxies are grouped together in these clusters, and the size of these largest clusters are actually are comparable in size to the smallest of the red dots you see here. So there is actually a scale match between the structure you see here and the structure you see here. But if we zoom into one of these little dots, we see that things can get rather complicated. Right? So galaxies are not just collections of matter. They have this structure in their gas, in their star formation, and we want to model both the formation of that large-scale structure that I showed in the previous slide and the detailed structure, the spiral arms, and star formation history of individual galaxies. And indeed, this galaxy is like the one we live in, so it's kind of important for us to understand how such a thing could come to be, because it's very important for us to come to be. And there's a fundamental problem with the connection between those two, and that is both the large-scale structure and the cosmic microwave background point to the existence of this strange stuff, well, several bits of strange stuff that we label cold dark matter and dark energy. And by dark, we essentially mean we don't understand what it is. Okay? The stuff we do understand, the stuff you and I are made out of, is just 4% of the energy density of the universe. And the rest of the stuff, whatever it isn't what we're made of. One of the successes of early cosmological simulations was to show that this dark matter was also not another thing we know about neutrinos. That's a subatomic particle that we have discovered produced by the sun and other nuclear reactions. But this is not that. And so what we have left are a bunch of fairly exotic candidates. Some sort of sterile neutrino. I was trying to explain axions to people last night, not very successfully. And a possible supersymmetric particle. Again, this is something that is outside our standard model of particle physics. And so since we have very little information about what this stuff is, even though it dominates the universe, we're trying to use the simulations to put constraints on what it is. Yeah?
I'm new to the field, but I am just curious, how did you get the split between 784? How do we even know the percentage of what we don't know?
Right. So the thing we do know is the total energy density. And that comes from basically Einstein's theory of relativity and measuring the curvature of the universe. So, the curvature of the universe can be measured. It tells you what the total energy density is. And we find that it's roughly 4 times more than the actual matter we see in it. And then, well, how do you know this dark matter is there? Well, the dark matter, we actually see its gravitational effect on galaxies and clusters of galaxies. Okay? So roughly, that's how we tell that these things are out there, even though we don't know what they are. But what is it? And we're hoping simulations will help us to answer that question. And here's the procedure. We know what the fluctuations look like in the very early universe. They're tiny. We can describe them with linear perturbation theory. But the galaxies we get out are these very nonlinear things, over densities of more than 1 billion. What we do know about it is that it's basically the self-gravity of these perturbations eventually turn into the galaxies we know about. And at least we do understand Newton's and Einstein's theory of gravity. And so that's the kind of thing we can plug into a computer, run the simulation forward from the cosmic microwave background. All kinds of interesting dynamics happen, and hopefully you get galaxies out at the end. For the cognoscenti, I should point out that these simulations, what we're really trying to solve is what the plasma physicists call the Vlasov equation. This is a 6+1 partial differential equation where the particles are actually sampling the six-dimensional phase space. So just aside from what we're actually doing. Furthermore, we have to solve this equation over a vast range of scales. And this is just to illustrate that. Here's a fair sample of the universe, actually a rather small sample of the universe. And an individual galaxy halo is a small portion of that. And we blow up a halo, and we see that the actual visual part of the galaxy resides only in the inner tenth of the total dark matter halo. And again, the existence of the dark matter halo has been confirmed by studying how the stars and gas in the galaxy rotate about its center, and it's part of the prediction of the cosmological simulations. And the substructure you see here actually goes all the way into the center. If you had dark matter glasses, this is what the central few hundred kiloparsecs of our galaxy would look like, according to a simulation by our student. This was a run on that Mare Nostrum that somebody showed a picture of earlier today. 1 billion particles inside a single dark matter halo run by Joachim Stadl from the University of Zurich and my former student. And so you've got a number of computational challenges, this huge dynamic range where we're looking at cosmological scales. We're talking hundreds of megaparsecs, where a megaparsec is a typical distance between pairs of galaxies, down to scales less than a kiloparsec, sort of the scale I showed you in that past picture. And of course, the typical distance between stars in our galaxy is roughly a parsec, just to give you kinds of scales we're looking at. And so you need this hierarchical adaptive gravity solver to handle that huge dynamic range. And the large range of scales also means a large range in time scales. The universe is 13 billion years old. We need to follow the entire history of the universe. But physics like star formation, that happens on mega-year time scales. And so we need a multi-stepping algorithm so that we're not advancing the large-scale structure on this star formation time scale. However, gravity is a long-range force. The force on an individual galaxy, or the stars within an individual galaxy, are influenced by much of the surrounding cosmological structure. And so you have to model that, and you need this hierarchical information that you need to pass throughout your simulation. So I mentioned stars, okay? So this is what our neighbor galaxy looks like, Andromeda galaxy. Again, this is very similar to our own galaxy. If we had dark matter galaxies, glasses, this is what the structure would look like. All right, so this does not look like that, okay? And that's because the gas, in particular, has different equations of motion than the dark matter. The dark matter is what we call collisionless. It does not interact. The gas shocks and cools, and we have to also model those hydrodynamic forces. And to do that, in the same framework, we use a technique called smooth particle hydrodynamics. We use this for several reasons. One, it can easily handle the high Mach number flows that occur in astrophysics. It can also easily handle the large density contrasts that I talked about. It's also a Lagrangian method. It can follow the matter as it collapses into a galaxy. A slightly esoteric but important point is that it's Galilean invariant. That is, as our galaxy is forming, the galaxy as a whole is moving at many hundreds of kilometers per second through the universe. And our code has to handle that without advective diffusion. Okay? And of course, in terms of a computational framework, it relies on particles, the same sort of particles we use for solving gravity. And just to give you an example of the importance of gas dynamics on this simulation, and by request, get the mouse over here, just to show you a little bit of how the gas interacts and plays an important part in the structure of a galaxy. So this is, the green material is the cold gas, and the red and yellow material is hot gas. Here's the timeline up here. Remember, the present day is 13 gigayears. This is the redshift where 0 is today. What's going on in the center of these galaxies? Stars are forming. As the stars die, they go supernova, where you have 10 to the 51 ergs of energy being blasted out into the gas. The multiple stars going supernova combine to produce these winds, which then blow the gas out of the galaxy, and which has several consequences, including what happens to the dark matter distribution in the center of the galaxy, and of course polluting the surrounding intergalactic medium. Anyway, just to show you the importance and the dynamics that the gas adds to the simulation. Okay, this is a slide. So how do we do the soluteup question?
What range of Mach numbers do these get?
All right, so sound speed for typical interstellar gas is, say, 10 kilometers per second. You have motions of hundreds of kilometers per second. So 10 plus. is the kind of Mach numbers we get. Oh gosh, this is not showing up. Yeah, black on dark blue. Great. So I just want to, many of you have seen this slide before, but just an illustration of how we do the gravitational interaction. Yeah. So we have a computational volume. I want to calculate the force on an object in this box, right? Normally, you think of gravity, the force on this thing is due to the particles in all these boxes, but we'll hierarchically divide the volume. So at the top level, we have these white squares, which represent the white nodes. At the second level, we have the yellow squares, which are represented by the yellow nodes in the tree, and so forth on down the tree, such that we get a few particles in each box when we're done the subdivision. And now when we go to calculate this force, instead of looking at every particle in this red box, we can consider this red box as a whole and just calculate a single interaction between that red box and the orange box. And so instead of calculating everything from this subtree, we just look at the parent node of that subtree, and we do the same for all the subtrees. So instead of having to calculate all these forces for this particular particle, we just traverse the tree and get a subset of the nodes. And that reduces the complexity of the gravity calculation from order n squared, that is in all pairs, to order n log n. And that's the Barnes hut that I discussed just an hour ago. We have a legacy code. That movie I showed you was actually from our legacy code, which implements it. We call it PKD Grav, and the gas version we call it gasoline. And in the process of creating that code and working with it over the years, we've come up with some particular issues that I enumerate here. The first issue is that most of the work for the calculation is done on the galaxy, which is a small piece of the actual computational volume. And so doing the load balancing so that each processor gets a piece of the galaxy can cause some systematic errors and actually increase the work. That is, it's not only the work that matters, it's also the size of the computational domain that makes a difference. Handling domain decomposition when you have some particles active and other particles not, it turned out to be an issue. And working where in the presence of large latencies turned out to be problematic for us, and our code only got good performance if we were running on a low latency network. And frankly, we got tired of porting our simulation to every new parallel architecture that came along. And so we turned to looking at ChaN++. Oh, but before I turn to ChaN++, let me just illustrate the problem with load balancing. Okay, so this is a typical galactic halo. Most of the particles are right in the center. And so if I want to load balance it, I want to sort of divide up the computational volume, as I've shown here, so that each processor gets a contiguous piece, but also gets a piece of the center. And the problem is that, say, this computational domain has to be opened up by, essentially, is large in one dimension, and therefore it has to be opened up by every other particle in the simulation. And so you get a huge communication overhead by having these long, skinny domains. So we turn to ChaN++. A couple things that attracted us to it initially. The ability to do this load balancing, I think, was the first thing that attracted us. And of course, the overlap of computing and communication that the virtual processors allow you to have. I think I mentioned this in the discussion. array-based parallel languages were not particularly attractive to us. We wanted something that could handle a generic data structure like a tree. And we wanted to be able to reuse some of our computational modules. And so being written in C++ was an advantage. And NAMD, the motion of atoms in a molecule is actually very similar to the motion of bodies in a galaxy. And so we figured, okay, if they can do well with NAMD, they might be able to do some things with our code as well. And so we started a collaboration with ChaNGa, like I said, about 10 years ago. In terms of the actual implementation, I won't bore you with the details. I'll just point out a couple of things. Well, the key thing is we used a lot of the charm functionality to do the latency hiding pretty much everywhere we could. All right, so there's the basic level of having multiple objects per physical processor. So if one object was waiting for data, another could be doing something. So that's the natural latency hiding that you get with charm++. But we went further than that, in that in each of these tree pieces, we further divided the work into these multiple units. And I list them all here, basically in order of priority. We start doing the off-processor gravity work, and if that runs out of stuff to do because it has to wait on data, then we can start doing the tree walk for the smooth particle hydrodynamics, which is slightly different data. And if that stalls waiting for data, then we can do the local gravity tree walk. And if we run out of stuff to do there, we can do the EWAL. This handles the periodic boundary conditions, very much like the EWAL particle mesh does for molecular dynamics. And so each of these, so essentially there's always work to be done if you happen to be waiting for data. And I should also point out that we use the composability aspect of charm, right? So the SPH walk is a completely different walk than the gravity walk, different opening criteria for cells, but we can have it running concurrently, essentially as a separate, what do you call it, separate char array, actually in a shadow char array. But still composable with the gravity walk. And furthermore, the things that really need high priority, that is, if a processor is asking you for data, that gets the highest priority so that this top walk isn't waiting forever. So again, we've got multiple features of charm++ that we use to help us scale our code. So this is just diagrammatically what I just talked about. We have a global work piece that is asking for off-processor data that actually goes through a cache manager so that if we request it once and somebody else needs it, we can reuse it. So there's a little amortization going there. And if we run out of global work, we can do the local work. And of course, we've got many tree pieces on an individual processor. That is something that one of the charm people wrote that was originally just in our code. Now it's a charm library. So it scales. What we have here is the core hours to complete a full gravity calculation as a function of the number of cores on the blue gene P. And the different lines are for different numbers of particles from 80 million down to 5 million. And then the solid is without the load balancer. The dotted is with the load balancer. And well, you see we're scaling out pretty well. So flat line is perfect scaling, and this is a strong scaling plot. And so you see we're doing pretty well all the way out to a point where we have just a few thousand particles per core. Compared with our previous code, well, we got maybe out here with a minimum of tens of thousands of particles per core in our legacy code. So it works. Oh, question?
What's going on with that 50 million load balance?
What's going on? So the short answer is I don't know. Let me just point out that the difference, so the 50 million is different than the 80 million in that these particles are a representative cosmological volume. The 50 million is, most of those 50 million particles are in the central 1% of the volume. So it's very hard to distribute the load, a hard load balancing problem, like I showed you on that previous plot. So it is a challenge. Not sure. So it's probably some communication issue that is popping out, is my guess. Yeah. So it's an opportunity. Yeah. Okay. So this has been implemented, and it is a production quality code. As it is. It has periodic boundary conditions for doing the cosmology, the multiple time stepping, the dynamic load balancing. We use CHARM's PUP to disk, migration to disk in order to do checkpointing, so we didn't have to write our own checkpointing. And we use CHARM's live-viz infrastructure so that you can do on-the-fly visualization of the simulation. Well, just to I'll skip a couple things. Just to point out that the multi-step performance also is doing reasonably well and not going out to quite as many cores. So this is on Ranger going out to 2,000 cores. Legacy code is the squares here, and the ChaNGa, you see, scales much better, particularly in the multi-stepping regime. Because of the better load balancing, essentially. Something that I did not anticipate when we started this project was the ability to use accelerators like GPUs, and so but that has been done. We use the hybrid API to speed up the gravity calculation, and we do each piece of the computer does the job it's meant to do. CPUs are really good at branching and things like that, so they do the tree walk. And when they're done their tree walk, they hand the data to the GPU, which does all that floating point to calculate gravity. But that's overlapped with more tree walk. So and this is the natural compute communication overlap that CHARM allows. Here we're applying it to the CPU-GPU trade-off. And so when you look at speed-ups on GPU clusters, this was for Lincoln, I believe, before it was decommissioned. So let's compare the pink line, where we only use the CPU, to the green line where we use the CPU and GPU, and you see we get roughly an order of magnitude speed up all the way out to 512 processors, and beyond. Just to let you know that it is being used for science applications. Collaboration with Victor Di Battista, we're looking at using ChaNGa to look at nuclear star clusters. This is a particularly challenging thing because, all right, we've got these star clusters and black holes in the middle of galaxies. The size scale is enormous, but somehow they know about each other. Their observational correlations say that the size of the star cluster of the black hole in the center of the galaxy is related to the size of the galaxy. How does it know? And so we're doing simulations to figure out how the formation mechanism depends on the size of the galaxy. It's a huge dynamic range, both in space and time scale. ChaNGa is ideal for this job. We're looking at clusters of galaxies. These are the largest bound objects in the universe. So they're very useful for studying cosmology because we can see them all the way across the universe. And so we can study the evolution of the growth of the universe, and hopefully that will tell us something about dark energy. But in order to do that, we have to figure out how you observe these things. One way to observe these things is in the how they perturb the microwave background. And this is a 90 gigahertz map of our simulated cluster. But again, you need this high resolution to do that job, and we will be comparing it, for example, with X-ray images of clusters. And then finally, we have a proposal in which we have informal, acceptance that we will be running a blue water simulation, studying galaxies as they're seen by the Hubble 12 gigayears ago. This is a prototype simulation, and we're trying to study their formation history to understand how you get pictures like this. So this is the Hubble Deep Field. There's only 2 stars in this picture. Everything else is a galaxy containing billions of stars. And we'd like to understand, why is this galaxy red and the other galaxy blue? Is the kind of issues that we want to understand. Right. All right. So there's some work to be done for the Blue Waters simulation. We are now on a timeline to complete it. And then and there's other cool stuff. We do need exaflop stuff to really do cosmology correctly. And then let me just finish with some of the features of CHARM++ that made all this possible, and take any of your questions.
Thank you, Quinn.
So how separated is the charm stuff doing the charm thing from the numerics? If I were to have an SPH code with my own sort of validated numerics, but I was interested in exploring charm, would I start with ChaNGa, or would I start by talking to these guys from scratch, do you think?
I think you would start with ChaNGa. That is, we tried to divide it up so that the SPH functionality is basically routines that you call. So that if you don't like the way I implemented SPH, you can just replace those routines. There might be a little bit of an issue if you want to change the way that I walk the tree, decide which is my neighbor. Although Pratish is trying to make that a little more easily modifiable. That's part of the motivation behind his DivCon framework.
Yeah, my question is related to SPH too. I was curious why you were using, or if there's any necessity to use the whole tree structure for SPH.
You use the tree to find your neighbor. So SPH involves what's called a summation over your nearest neighbors. And so you have to find them. And in a situation where you have large dynamic range of interparticle separations, a tree is probably the most efficient data structure to do that.
Instead of, I guess a mesh would be for more uniform distribution.
Yeah, if you use a mesh, that would only work if you had a uniform distribution of particles. Thank you.